We will learn about the basic structure and characteristics of resonators, crystals, and oscillators, which are clock elements used in MCU applications, as well as the main specifications and applications of the most commonly used crystals. The clock is an important component that plays the same role as the heart in the human body. Just as the heart must beat to move the hands and feet, breathe, and perform other activities, the system cannot perform any actions without a clock. In all embedded systems, including computers, this clock must be supplied. Let's learn about the types of clock oscillators. Clock generators are classified into three types: resonators, crystals, and oscillators. A ceramic resonator is a device that generates an oscillation frequency using a piezoelectric ceramic. The piezoelectric ceramic oscillator is a structure that generates a clock signal of a specific frequency by being connected to the oscillation circuit inside the MCU. The internal equivalent circuit is similar to a crystal oscillator, and is an integrated device configured by connecting capacitors to both ends of the piezoelectric ceramic, and is a three-terminal passive oscillator consisting of two terminals for the clock and a ground terminal. Although the frequency deviation is somewhat larger than that of a crystal, it has the advantage of being able to simply configure an oscillation circuit without additional external components. A crystal oscillator is a device that uses the oscillation characteristics of a specific frequency according to the structure or shape of the crystal. It is a frequency generator that supplies a stable frequency, and is a passive oscillation device that generates an oscillation signal of a specific frequency by connecting an oscillation circuit inside the MCU and an external capacitor. An oscillator is an active oscillator that generates a clock when connected to power and ground by integrating a crystal and an oscillation circuit or IC. In addition to general standard oscillators, there are high-precision TCXOs, VCXOs, and OCXOs, which have very precise oscillation frequency characteristics of approximately 1 ppm or less. Comparing the characteristics of the three oscillators. The oscillation frequency ranges from up to 50 MHz for the resonator and up to 100 MHz for the crystal and oscillator. Frequency accuracy, or deviation, is approximately 500 ppm for a resonator and approximately 50 ppm for a crystal, so the crystal has approximately 10 times the precision of a resonator. And in oscillators, TCXO and VCXO are mainly used for high-precision applications at less than 1 ppm. The resonator uses a thin film piezo using lead zirconium titanate, and the crystal oscillator uses a crystal. The oscillator is a structure that combines a crystal and an IC for temperature or voltage compensation or an oscillation circuit. Resonators are generally used in systems with low speeds or no external communication interfaces, while crystals are applied to most embedded systems due to their stable oscillation frequency characteristics. In oscillators, TCXO, VCXO, and OCXO are applied to systems that require high-precision frequencies such as smartphones, measuring instruments, and communication equipment. For USB communication, it must have a frequency stability of 500 ppm, for Ethernet, 100 ppm, and for communication such as Wi-Fi, Bluetooth, and LTE, it must have a frequency stability of less than 20 ppm. The price is that resonators are cheaper than crystals, while oscillators are more expensive and consume more power. A crystal oscillator is a device that uses the oscillation characteristics of a specific frequency according to the structure or shape of a crystal. It is used as a frequency generator that supplies a stable frequency and is used in almost all electronic products around us, such as various electrical and electronic devices, measuring instruments, and PCs. These crystals come in various packages, including dip type and SMD type, and can be used as reference frequency generators from tens of kilohertz to tens of megahertz. The equivalent circuit of the crystal is the R/L/C equivalent circuit of the crystal oscillator itself, and the shunt capacitance between the two electrodes of the crystal element is equivalent to C0 and has a value in the range of 2 to 7 picofarads. This equivalent model of the crystal itself and the capacitor connected to the two external terminals are combined to produce an oscillation action of a specific frequency. Let's take a look at the main specifications of the crystal unit. Frequency refers to the oscillation frequency of the crystal, which is the most important parameter. And frequency tolerance refers to the plus or minus allowable frequency deviation from the specified crystal oscillation frequency. It is usually expressed in units of ppm at room temperature of 25 degrees. Load capacitance CL is the capacitance value when the crystal is connected to an external circuit, that is, two capacitors, and operates at a normal oscillation frequency. In other words, it means the equivalent capacitance value when looking at the two terminals of the crystal when connected to an external circuit. Shunt capacitance C0 refers to the capacitance value that exists equivalently between the two electrodes of the crystal. Drive level refers to the power consumed by the crystal and indicates the maximum power value under normal operating conditions. Crystals are mostly used as the reference frequency of MCUs. Therefore, all MCUs must have two terminals for crystal oscillators. And it is common to use them by connecting a crystal and two capacitors externally, with an inverter and feedback resistor inside. An oscillator circuit with this structure is called a Pierce oscillator. Then how do we determine the value of the external capacitor connected across the crystal? The crystal datasheet provides the load capacitance, CL, and the shunt capacitance, CHARO. The capacitance value of the externally connected capacitor can be determined based on the CL and CHARO values on the datasheet. The equivalent capacitance when looking at both ends of the crystal from the MCU side is called the load capacitance CL. Above, you can see the internal shunt capacitance CHARO of the crystal itself and two capacitors connected between the two crystal terminals and ground, and additionally, you can see the stray capacitance C stray due to the PCB pattern on the two crystal terminals. Here, to obtain the capacitance CL, looking at it from the perspective of the two terminals of the crystal, the external capacitors CE1 and CE2 are in series. And C0 and C stray are connected in parallel to the two ends of the crystal, so the relationship between the parallel conversion values of capacitors CE1 and CE2, plus C0, and plus C stray is 1. Since the external capacitors CE1 and CE2 are generally the same value, CL becomes the relationship 2. Therefore, the external capacitance CE becomes the relationship 3. Which is the load capacitance CL, minus shunt capacitance C0, and minus C stray multiplied by 2. Stray capacitors are parasitic capacitances due to the pattern of the crystal pins, and have a value in the range of 2 to 4 picofarads depending on the pattern structure. So if we assume it to be 3 picofarads, the external capacitance CE to be connected to both crystal terminals can be roughly calculated by the relationship of load capacitance CL, minus shunt capacitance C0, and minus 3 picofarads times 2. Since most of the MHz crystals use the SMD type, we will look at the parameters of the major manufacturers' crystals. Focusing on the standard package 32254 pin type and the 5032 and 60352 pin types. The crystal is used as the main clock of the MCU, so the frequency deviation must be small, and is generally around 20 ppm. The shunt capacitance of the crystal itself, CHARO, has a value of less than 7 picofarads, and the load capacitance has a unique standard value for each manufacturer within the range of 8 to 32 picofarads. The shunt and load capacitances are specified on the datasheet. Stray capacitors are parasitic capacitances caused by the pattern of the crystal pins, and have a value in the range of 2 to 4 picofarads depending on the pattern structure. Assuming it to be 3 picofarads, you can calculate the external capacitance value to be connected to the two crystal terminals. In other words, the C value of the external capacitance CE to be connected to each crystal terminal is twice the load capacitance minus the shunt capacitance minus 3 picofarads. In the case of the Avericon ABM3 series, the capacitance of CE is 18-7-3 is 8 picofarads, so doubling it will be 16 picofarads. After applying the external capacitance value with this calculated value, it is good to check whether the MCU is operating normally and also check whether the correct frequency is output by the measuring instrument. The frequency decreases as the external connected capacitor CE value increases, and conversely, the frequency increases as it decreases. You can understand that the frequency is based on the general formula of 1 divided by 2 pi root LC. In other words, if you adjust the clock frequency very precisely, it will be helpful to know this concept and tune it. This time, we will look at the parameters of major manufacturers' products of 32.768 kHz crystals for real-time clock, or RTC, purposes. Crystals for RTC are used in applications that utilize real-time information by maintaining real-time information with a backup battery even when the MCU is powered off. For accurate date and time information, the frequency deviation must be small, typically around 20 ppm. The shunt capacitance of the crystal itself, CHERO, has a value of less than 1.5 picofarads. And the load capacitance has a unique standard value for each manufacturer within the range of 6 to 12.5 picofarads. These shunt and load capacitances are specified on the datasheet. Stray capacitors are parasitic capacitances caused by the pattern of the crystal pins, and have a value in the range of 2 to 4 picofarads depending on the pattern structure. Assuming it to be 3 picofarads, you can calculate the value of the external capacitor CE to be connected to both crystal terminals. In other words, the value of 2 times the load capacitance minus the shunt capacitance minus 3 picofarads is the value of the external capacitance CE to be connected to each crystal terminal. In the case of Avericon ABS05, 12.5 minus 1.3 minus 3 is 8.2 picofarads, so if you double it, it will be approximately 16 picofarads. After applying the external capacitor capacity value as calculated in this way, it is recommended to check whether the MCU is operating normally and also check whether the correct frequency is output with a measuring instrument. In summary, the value of the external capacitor of the crystal, CE, has a relationship of twice CL minus CHERO. Here, considering the stray capacitance due to the PCB pattern of the crystal pin, it should be set slightly lower than the value according to the relationship. For example, if the load capacitance is 18 picofarad and the shunt capacitance is 7 picofarad, then 18 minus 7 is 11 picofarad, so you can specify a value less than 22 picofarad as the external capacitance value. If the crystal signal line on the PCB pattern is long, the stray capacitance increases, so you should design it as thick and short as possible. The crystal should be placed as close to the MCU as possible, with the signal trace length as short as possible, and should not cross or pass through other signal lines. The area around it should be surrounded by a ground plane to reduce noise radiation. In the case of multi-layers, the inner layer under the crystal should not be passed with ground or signal lines. and it is recommended to configure the bottom layer as a ground plane for shielding effect. Since the origin of most EMI noise is likely to be the frequency of the applied crystal or its multiple frequency, pattern processing around the crystal is important.